Hello, everyone, and welcome to MOOC 11, Session 3. This is Andreas Antonopoulos, and I'll be answering your questions from the last week's sessions and all of the learnings you have learned. Let me just quickly check into the chat room and make sure everybody can hear me OK. If you could just holler on the chat room and let me know if the video and audio is coming through clearly. About a 30-second delay. Let's see. Yes, we've got good sound. Fantastic. Yanis asks, how am I sure that a private key is generated at random? Well, this is a really good question, Yanis, because it's actually fairly difficult to evaluate randomness. So in terms of generating random keys, you have to trust that the software and the device that you're using that software on is doing the necessary things to generate good quality entropy, good quality randomness for your keys. So for example, hardware wallets have built-in random number generators. Your operating system has a built-in secure random number generator. And if your software running on your computer uses it correctly, then that will be high-quality randomness. Ultimately, there's an element of trust there. However, you can actually generate seeds and keys on your own by essentially using natural randomness. This is an exercise more for those who are either extremely paranoid or just want to see how this works. But effectively, what you can do is you can use playing cards, you can use dice, you can use other things like that in order to generate a private key. Private key is just a number. And that applies also to generating a seed for a hierarchical deterministic wallet. And you can do that in terms of generating the entropy for 256 bits by flipping a coin 256 times and writing down 0, 1 for heads and tails. And you've got basically your private seed entropy, 256 bits of randomness. Yanis also asks, when transactions are broadcast to the network, the SHA-256 function is used to verify data integrity mean? Well, one of the really useful functions that cryptographic hashes offer is the ability to produce a fingerprint, a cryptographic fingerprint. So the way a hash function works, a cryptographic digest or cryptographic hash function, is that it takes an arbitrary length data stream of bits, basically, and converts it to a fixed length number. Now, for example, SHA-256 will take any amount of data and convert it to a 256-bit number. And that 256-bit number depends on every bit in the source data in such a way that even a small change in the source data, just 1 bit change, will lead to a very large change in the outcome, in the fingerprint. And that's one of the characteristics of cryptographic hash functions that allows us to do something very interesting, which is produce fingerprints. Now, if you want to confirm that a data hasn't been modified since it was created, and this applies, for example, to a file on your computer, it applies to a picture that you want to make sure hasn't been modified, or PDF documents, you could use a cryptographic function like SHA-256 to produce a 256-bit fingerprint. And as long as you can check that again, you can make sure that it hasn't changed. In the case of transactions, the transaction itself is hashed using the SHA-256 function. And in fact, it's double hashed. And the result is called the transaction ID. So when you see a transaction ID, that transaction ID is produced by hashing all of the data in the transaction using a specific formula. And that acts as a fingerprint. That transaction ID doesn't change. So you can't change the transaction without effectively changing the transaction ID, its fingerprint. And so that way you can ensure that the transaction hasn't been changed. Cryptographic hashes are also used in digital signatures, meaning that when you sign something with a digital signature, you don't sign the data itself. That would be inefficient. Instead, what you do is you sign a hash of the data. And if you sign the hash of the data, you're essentially taking the fingerprint that summarizes the data in a way that can't be changed. And then you put a digital signature on that fingerprint, certifying that that was signed by you or your private key. So both of those techniques used together produce the integrity that you need in a transaction. The signatures within a transaction validate that the private key was used, so it shows that an authorized user created this transaction, the person who was authorized to spend the Bitcoin. And the transaction itself can't be modified because its fingerprint has been signed, and you can't modify the transaction without modifying the fingerprint, which then, of course, invalidates the signature. Yanis asks a related follow-up question, which is, many wallets offer an option to sign a message. What does this mean, and how is it displayed on the blockchain? Does it have anything to do with sending funds? A great question, Yanis. The option to sign a message that you find in many wallets is the option to take an arbitrary piece of data, which could be, for example, a text message, that you could compose by writing a little text message, and then use the private keys controlled by your wallet to apply a digital signature to that text message. Essentially, it signs a cryptographic hash fingerprint of that message. So you could write a message that says, on this day, I, Yanis, approve, something. Or on this day, I, Yanis, testify that this happened. And then you use one of your private keys from your wallets to sign that. And somebody else, if you send them the signed message, somebody else can then verify against your Bitcoin address that this, in fact, was signed by you. So you're basically using the private key, public key cryptography to sign messages that are not transactions. This has nothing to do with spending funds. This has nothing to do with signing transactions. It's the same technique. It's the same technology as you use to sign transactions. But instead of signing a transaction that you present to the blockchain, and the blockchain uses that to verify that you want to spend funds, you're signing a text message that you present to whoever you want that proves that you were willing to sign that text message and whatever it says inside. It's not included in the blockchain. It's not transmitted to the blockchain. It simply creates a signed message. For example, you could say, I am Satoshi Nakamoto, and then sign with the keys that are in the Coinbase of the Genesis block. And that would prove that you have control over those keys. It wouldn't actually prove that you are Satoshi Nakamoto. It would only prove that you have the keys from that Genesis block. It's the kind of simple proof that could be implemented by someone claiming to be Satoshi Nakamoto, for example. And it tells us a lot when that kind of simple proof is forged. Yanis has a third question. How can I manually construct a transaction with multiple inputs, or is this being done by the blockchain? Yes, you can manually construct transactions, and you can do that with a variety of wallets that allow you to manipulate the transaction on a very fine level. For example, the Electrum wallet, as well as many web-based wallets and command line wallets, allow you to control the construction of the transaction down to which inputs are included. So you can do that manually. This isn't done by the blockchain. It's done by wallets. And some wallets will allow you to do that. Of course, most wallets don't. They do this for you. So they will select inputs based on an algorithm that allows them to construct a transaction that is not too expensive or too bloated. So for example, if you have exact change, then you're going to use that input to make your payment, considering fees, of course. But if you don't, and you need more than one input in order to make a payment because you have lots of smaller amounts in your wallet, then your wallet will construct a transaction with multiple inputs so it can put together enough money to make the payment that you're trying to do. So that's how these transactions are constructed. You don't have to do it, but you can with some wallets. This is also called, in many cases, you'll see it in a menu or an option in the wallet called coin selection. And the ability to do coin selection is basically this: to construct a transaction with multiple inputs where you manually select the inputs. All right, let me take a quick sip of coffee here, check in the chat room, see how everybody's doing. Hello from the Netherlands. Hello from Vienna. Hello from Switzerland. Hello from Greece and Indonesia and the British Virgin Islands, Cordoba, Argentina, Crete. Wow, all over the world. Hello, everyone. Hello from Tanzania and Nairobi. Nice to see you all. And hello from Brazil. Fantastic. So I've said hello to everybody. Everybody's smiling now and sending even more places. Spain, New York, yes, London. Fantastic. What a great team this is. Next question. Christina asks, regarding the matter of Quadriga CX and the funds that are lost as the owner died holding the keys, how can you see this affecting encryption and regulation? It's an interesting question. Christina, Quadriga CX is a Canadian exchange that recently went into bankruptcy proceedings in order to protect itself legally while it tries to find where it can get its funds to pay back its customers. And the story apparently at the moment, as far as we know, is that the owner of the exchange had sole control over keys that were what's called cold storage, which means that these were the long-term store of Bitcoin that are not put offline for security reasons, they're not put online for security reasons. And apparently the owner of Quadriga CX was the only person with access to these keys. They died recently, and as a result, those keys are now lost. It appears they were stored on an encrypted laptop or something like that. I mean, this is a perfect example of the risks of third-party custody over keys. I've used this expression many, many times. You've probably heard it being chanted as a mantra, not your keys, not your coins, or not your keys, not your Bitcoin, not your keys, not your crypto. Basically, the same idea is that you should be very careful trusting third parties to hold your money. This applies to any domain of money, but it applies especially with cryptographic digital money because it's actually easier to steal Bitcoin or other cryptocurrencies when you put it all in one place and control it by one person. It's also easier to lose it. Bitcoin and other cryptocurrencies maintain their security through decentralization. The idea is that if in order to rob 1,000 people, you have to break into 1,000 wallets on 1,000 different computers, some of which are hardware, mobile, software, desktop, etc., that's very difficult to do. You have to pull off essentially 1,000 heists. But if those 1,000 people deposit all of their crypto and give that crypto to one person who controls all of the keys, now you only need to hack one wallet in order to get 1,000 times the keys. Or only one set of keys needs to be lost for 1,000 people to lose their money. And this is exactly what's happened in this case. How does it affect encryption and regulation? It doesn't, really. It doesn't change anything about either of those categories. It's arguably, as I said when I did my testimony to the Canadian Senate, it's important to think about institutions that hold Bitcoin on behalf of other people, custodial accounts like that, as very similar to banks, and put them under the same type of scrutiny because they concentrate risk. And they have control over people's funds, and that introduces significant risks. Risks of resilience and contingency planning and disaster recovery and business continuity, in the case of a founder's death, for example, but also theft and hack and reserves and whether they actually have the money that they claim to have. And as I've suggested, regulating the decentralized control over keys is unnecessary, and regulating the centralized control of keys is both necessary and something the government should be doing. But of course, we don't see that in the space. There's a lot of sloppy security. So hopefully what this does is it doesn't change encryption. It doesn't change regulation. Really, what it does is it teaches people the lesson again that apparently needs to be told again and again and again and again. And we need to see exchanges fail again and again and again before people learn the fundamental lesson of not trusting third parties with their cryptocurrency. Dario asks, in theory, a quantum computer would be able to generate a private key based on a public key, essentially reversing the elliptic curve multiplication function. This is known as solving the discrete log problem. What are the actions that are being carried out to solve this situation? So Dario, first of all, we've got to understand that while theoretically a computer can reverse elliptic curve cryptography, it can only do so if it has the ability to marshal many quantum bits. A number of quantum bits required to break elliptic curve over 256-bit prime number is a lot. I don't know what the exact estimates is. I think it's about half the key space. I think you need 128 qubits. We are perhaps decades away from 128 qubits. Nobody really knows, but quantum computing isn't progressing that fast. So first of all, it's important to understand that this is very much a theoretical attack. Even if you assume state-level actors that have significant advancements over quantum computing that they're not sharing with the rest of the world, and even in that case, it's unlikely they've achieved a level of quantum computing that can break these things. Even if they have achieved a level of quantum computing that can break these things, at that point, they can also use that technology to break all military encrypted communications around the world and all of the command and control systems that control things like nuclear weapons and submarines and aircraft and things like that. At which point, this is a fearsome weapon that needs to be kept secret, because having that ability and people not taking countermeasures is a significant strategic advantage. And the reason that's important is because you can take countermeasures. And there's a number of countermeasures. One of them is to use a quantum signature algorithm in order to thwart quantum computer decryption. So there are algorithms that are resistant to quantum cryptanalysis. And more algorithms will be discovered. And if you actually have the ability to do desktop quantum computing, even with just a few qubits, then you could use a quantum computer to do the signatures and the encryption, perhaps in the form of a hardware wallet or inside your laptop, at which point a quantum computer can't easily break that. So this is an arms race. And encryption, cryptography, security in general is always an arms race. There is always the possibility that an algorithm or cryptographic system will be broken. And every cryptographic system has a shelf life. It has a maximum life expectancy, after which it becomes weak because either new models for attacks are discovered or because the state of computing advances enough to be able to brute force economically these algorithms. We've seen that happen with the data encryption standard. We've seen it happen with MD5. We've seen it happen with SHA-1. Effectively, all encryption algorithms eventually die. So the question is, what do you do about that? And there's a number of answers to that, including changing the digital signature algorithm, which is quite possible with these systems. Nothing is fixed within Bitcoin that can't be changed in terms of cryptographic algorithms. Some of the principles are not going to get consensus. Like, you can't change 21 million as the maximum issuance of coins. Nobody's going to agree to that. But if you face the threat of a quantum computer breaking your digital signatures, that's the kind of thing where you can get broad agreement from the ecosystem to change the signing algorithm. And when that becomes necessary, it can be done. There's one other little catch here, which is that public keys that can be reversed to private keys with this theoretical quantum computer, you've got to realize that public keys are not actually published on the blockchain until a wallet is spent or an address is spent. Meaning that when you send to a wallet, what you put on the blockchain is its Bitcoin address, which is not its public key, but in fact is a hash, a double hash of the public key, and you can't reverse that hash. Hash algorithms are far less susceptible to quantum computers, which means that Even if you had a quantum computer that could reverse a public key to a private key, that same quantum computer could not easily reverse SHA-256 to the public key, which means that the only time you'd have an opportunity to reverse a public key was after someone had tried to spend from that key, at which point they published the public key in order to validate the signature. So that's the only time a public key is shown. Now, if you follow good practices in Bitcoin, you only ever use an address once. And so when you spend it, the moment the public key appears on the blockchain and a quantum computer can start cracking it, it no longer contains any balance because you've already spent it to another address, which again is protected by a hash, not a signature. So in fact, there is another layer of protection built in that protects us against quantum computing. Quantum computing is not a practical consideration for security in any blockchain today. It may become a practical consideration over the next decade or so, and there are plenty of solutions to address it when that happens. Checking in with the chat room. Hello from Texas, from Spain, from Idaho, from England, from Benin, from Nigeria, from India, from Madrid, from Tanzania again. Hello, everyone. It's nice to see such a really international group of people joining me for this course. Fantastic. All right, let's go to the next question. David asks, oh, no, sorry. Let's go to the next question. Scott asks, if I have an ASIC miner and I get a reward, how is this technically linked to a wallet of mine? Can you explain the process I should follow? That's a great question, Scott. How does the network know who to pay when you win a block? It's really quite simple when you think about it. When you have an ASIC miner, you construct a candidate block that is the block you're going to try to find a proof of work for. And that candidate block is made by your own computer. So your computer that's connected to the ASIC miner that is collecting transactions and blocks off the network is going to construct a candidate block by taking a whole bunch of transactions that are currently unconfirmed, stuffing them into a block so you can make some fees, and basically building the block. You're proposing a new block to the network. You don't show this to anyone until you have proof of work, because no one's interested in a block that doesn't have proof of work. You just send it to your ASIC miner. So within that block, there's a transaction. That's a special transaction called the Coinbase transaction, and that's the transaction that pays the mining reward. Who creates that transaction? Well, your computer creates it. So when you're a miner, your computer creates the candidate block, and your computer creates the Coinbase transaction, which represents your 12.5 Bitcoin reward plus whatever fees from all of the transactions that are in there. And therefore, you decide who that transaction pays out to. Your computer puts your own wallet's destination address into that candidate block when you're mining. If you're mining as part of a pool, the pool operator does that. But if you're mining by yourself, for example, which you probably would only do if you had a lot of mining equipment, you would have your computers construct candidate blocks that already have a Coinbase transaction in them that pays you. So you write that transaction. So effectively, miners write a check to themselves to collect the reward. But the key to understand here is that that check isn't valid unless the block in which it was written is valid. And that only happens if they find proof of work. So when a miner verifies and finds a proof of work solution for a block through mining, once they've created a valid block, then the blank check they wrote to themselves for 12.5 Bitcoin plus fees in the Coinbase is now a valid transaction. And if that block is accepted by the rest of the network, then that transaction exists in everybody's blockchain, and it shows clearly that this miner is being paid their reward. Of course, the reward needs to be the correct amount. It needs to be exactly the same as the fees and the block subsidy at this level. Everything in the block has to be valid. Otherwise, it's rejected. But if it is valid, then there you go. The miner has paid themselves by writing a check, putting it in a block, finding proof of work for that block, and then telling everybody else so that everybody else writes that block to the blockchain. And at that point, 100 blocks later, the miner can now spend that transaction. There's a 100 block limit for Coinbase's transactions. They can't be spent until 100 blocks have passed. Essentially, a miner's own Coinbase transaction has to have 100 confirmations before it's spent. And this rule is to prevent miners from using chain reorganizations to double spend their own rewards. David asks, when a miner creates a block, am I right in thinking that this block is then transmitted to all other nodes on the network and is available for any miner to validate? Well, no, not exactly. It is transmitted, but only after the proof of work is found. So a miner only transmits a block to other people once that miner has already validated and proven that block by finding a nonce that creates proof of work for that block within the difficulty target, meaning that the miner has to do quadrillions and quadrillions of hashes in order to find a suitable nonce. Only once that block contains a correct nonce that produces a correct proof of work can the miner send it to the rest of the network. And the reason is because when the miner sends that block, the very first node they send it to will validate that block. And if it doesn't have proof of work, it will reject it and, in fact, disconnect from the miner that lied. So every node on the network validates every transaction and every block, which means that miners cannot propagate blocks until those blocks have been made valid. And that means they have valid proof of work. David asks, what is the predetermined target created for each block? I assume this value then travels with the block. Yes, each block contains a target difficulty. And this is validated by every node because the target difficulty for the entire network should be the same. And so the proof of work contains within it essentially the target difficulty. So every node can validate that the block has been mined correctly and its proof of work is within the target. Jen asks, is the following scenario possible? Could a hacker change the client software of Bitcoin Core so that it would accept fraudulent updates? Then everybody downloads the new update. Then the majority of honest miners, without knowing, become dishonest miners and propagate fraudulent transactions. Which is the real Bitcoin then? Is it the chain with more proof of work or the one without fraudulent transactions? Jan, this scenario is not possible. And the reason it's not possible is because of several safeguards that are in place. First of all, updates to Bitcoin Core software are not done automatically. You don't have the client downloading an update to itself, because that would provide a vector for someone to compromise all of the mining nodes and all of the network nodes in the network in one go, which is, of course, why there isn't an option like that. So miners have to manually download and update or upgrade their mining software and their node software when they decide they want to update it. Clearly, since miners are spending hundreds of thousands of dollars of electricity or even millions of dollars of electricity mining, they're not going to just risk that with any old software that might produce invalid blocks and therefore cause them to lose all of this money. So there are incentives in place to make sure that miners are very careful about upgrading their software, because if they introduce a bug, they lose a lot of money, and they lose money every hour that they're mining with this buggy software, because all of their blocks will get invalidated by everybody else. So honest miners remain honest by carefully checking their software, and that means testing that software extensively before pushing it into the mining rigs. Effectively, software updates are not done in one step. They're done on test networks and then validated with some of the miners and then pushed gradually out to the infrastructure. And at the same time, the same thing happens for network nodes. So operators of network nodes, users, people running exchanges, people running merchant services, people running all of these other infrastructure services do not just willy-nilly upgrade the nodes whenever they decide without validating those nodes and making sure that the software still operates correctly. So it has to go through a series of, and the upgrades don't happen simultaneously. The network at any point in time runs 5 or 6 different versions at least of the software. So at any moment in time right now, let's say my node is running version 0.17.2 of Bitcoin Core. There are going to be nodes out there running 17.1, 17.0. There's probably some nodes running v16. There might even be some nodes running v15, which is two versions behind, as well as other implementations of the Bitcoin software that are not Bitcoin Core. And all of these are following the same rules, which means that if one of them went astray, the rest of the network would reject those blocks and transactions and keep it in check, forking it off if necessary and disconnecting it from the network simply by rejecting its transactions and blocks. Because the ecosystem has some diversity of versions as well as diversity of clients, and because upgrades don't happen simultaneously in a coordinated fashion, but instead they roll out with every party that has economic incentives doing due diligence and testing, the scenario where someone can compromise this is impossible to pull off. That's not even counting the fact that all releases of the Bitcoin Core software are PGP signed by the maintainers. All of the Git commits are PGP signed. And there's a system called a deterministic build system that produces executables that contain digital signatures that can be validated, where you can run software to build the Bitcoin Core software with a standard configuration, a deterministic build as it's known. And then you can prove that the resulting binary is the same as the binary that everybody else built and therefore hasn't been compromised in any way. So you can basically trace trust in the software from the binary to the source code, to the commits that were made by various maintainers, to the commits that were made by various developers, and identify what changes were introduced by whom. So there's a lot of infrastructure to prevent this kind of compromise. Sergio asks, and I think this is the last question we have, so I'll also expect you to ask me some additional questions on the chat room. Actually, there's a good question right here, which is about the nonce. I talked about the nonce before. And so let me explain what the nonce is in mining. Now, we've talked about cryptographic hash functions. And what cryptographic hash functions do is produce a specific fingerprint from data such that if you make a tiny change to the data, just a single bit, no matter how big the data is or how small the data is, it will produce a radical change in the fingerprint, allowing you to determine that, in fact, the data has changed. So when you produce a hash, the hash is completely different, a completely different number, even if all you changed was 1 bit in the input. So what hash functions are doing, essentially, is it's like taking all of the bits of your data, pouring them into a bucket, and then stirring them algorithmically. So effectively, a cryptographic hash algorithm just stirs up the bits. If you look at how the algorithm works, what it's doing inside is a lot of addition. So it's adding up binary numbers. And it's doing those additions with a modulo, so that if you add up to more than 32 bits, it wraps around and starts again. Which mixes those bits effectively, as well as binary shift operations, where the cryptographic hash algorithm will take a chunk of bits and will shift them left or right, and then add them to other bits. And essentially what it's doing is shuffling. So it's a bit like shuffling cards, right? So you take the data that you put in to the cryptographic hash algorithm, and you cut it into chunks, and then you mix those chunks together. And you keep mixing them and mixing them until eventually you get a 256-bit number, which is the output of your cryptographic hash, which is the fingerprint. Now, any point in that mixing process, if one of the bits of the data is different, it causes the mixing process to go down a completely different path, which produces a completely different fingerprint. So just changing one bit changes the cryptographic hash function. So, but if you think about it, the cryptographic hash function, its output, the number it produces, the fingerprint it produces, is effectively a random number. It's a random number in that you can't predict what it's going to be, but it's also a deterministic number, meaning that if you put the same data in every time to the same algorithm, you'll get the exact same fingerprint, which means it's very easy for anyone to verify. If you take the data, put it through the fingerprint algorithm, you get the same fingerprint as everybody else who puts the data into the hash algorithm. So this is a very interesting trick. You put a data in. If you change it even by a tiny bit, it seemingly produces a completely different random number. But if you present the same data to someone else, and they put it through the fingerprint function, it's going to produce the same fingerprint. So what if, when you're trying to pick these random fingerprints that are coming out there, you set a target and you say, listen, I want my fingerprint to start with 0. OK, so what are the chances that your fingerprint starts with 0? Well, if you're looking at it in binary, and the first digit can either be 0 or 1, then if you just keep throwing fingerprints out there, half of them are going to start with 0, half of them are going to start with 1. So you've got about a 50-50 chance, right? What about both of the first binary digits being 0? Well, in that case, you've got a 25% chance, because only 1 in 4 of the results is going to have both of the first binary digits being 0. So you keep throwing fingerprints, and you keep hashing. And the hashing results, 1 out of every 4 hashing results is going to start with 2 binary 0 digits at the beginning. And then you can keep going with that. Every time you add the requirement for 1 more 0, you get half as many of the hashes fit that target. So now you've gotten to 30 zeros. Well, now only 1 in a quintillion hashes will actually have all 30 of the first binary digits be 0. And so in order to find that one, what you have to do is take your data, which is your block, modify it slightly, calculate the hash, see if it has 30 leading zeros. It won't. Try again, try again, try again a quintillion times, until by complete chance, the one tiny little tweak you made to the input data produces a hash that starts with 30 zeros. So what is the nonce? The nonce is the part of the block that you're changing. So if you think about the block header contains a timestamp, it contains a block number, it contains the Merkle root of transactions, which is kind of like a fingerprint of all of the transactions in the block. It contains the hash of the previous block. All of this information is fixed, right? So for a valid block, all of this information can only be one thing. You can't really change it. You can change the timestamp a tiny bit by a few seconds here and there, but the rest of this data can't be changed. It's, the previous block is always going to be the same number. The fingerprint of all of the transactions is always going to be the same in that candidate block that you've built. Well, there's a special part of the block that's 32 bits that doesn't do anything in the block. It's just sitting there. And you can put any number you want in there. Why does that space exist? It exists to allow you to change something in the block header so that you can produce a different hash. So we call that the nonce. So let's say you take this 32-bit number, and you start it with all zeros, and you hash the block header, and you get some kind of hash. Does it have the necessary number of zeros in the beginning to meet your target? No. Try again. So instead of 0, let's make that 32-bit number, let's make it 1. And then 2, and then 3, and then 4, 5, 6, 7, 8, 9, 10. And as you keep incrementing that 32-bit number, every time you hash it, it produces a completely different fingerprint. You do that 5 quadrillion times, and eventually you produce a hash that starts with 30 zeros just by chance. And when you do, what you can then tell everyone is, here's a block, and look what I found. If you put this nonce in, and this nonce is, oh, it just happens to be the number 6,475,322. If you put 6,475,322 into the block header, watch what happens. You hash that, and the hash, by complete coincidence, has 30 leading zeros. And how do you know that it took me a lot of time to find that? Because you know that the only way I could do that was by plugging numbers into the nonce and hashing and waiting to see if the result matched. So that's what a nonce is. It's simply the space in the block that has no meaning, where you can just plug in a random number and keep trying in order to find a specific fingerprint, to produce a fingerprint. And then once you tell everybody that random number, they can all plug it into that space in the block where it does nothing. And when they produce the fingerprint for the block, it's this magical fingerprint that has this special pattern of zeros in the beginning. And they're like, oh, wow, it must have taken a lot of work to find that random number that you have to plug in, the nonce. And that is proof that you did the work, proof of work. So that's how a nonce works. Now, there are some complications. 32 bits is not enough to do all of the hashing you need. So miners actually use some additional space in the Coinbase that doesn't do anything. For changing some bits there. They also use part of the timestamp because they need to move a lot of bits in the input to produce that. So the nonce isn't just in one place, but that's a more of an implementation detail. So that's how nonces work. Let's see if we've got any more questions in the chat room, and then I've got one more from Sergio. All right, a couple of follow-up questions on that, which I find interesting. So really good questions in the chat room today. So talking about nonces, Luke asks, do the miners know the amount of zeros required for the next block? Yes, that's the target difficulty. So the target difficulty is how many zeros does the hash have to have? And in simple terms, that means in binary. But you can just think of it as a number. So if I say that a number starts with so many zeros, effectively what I'm saying is that that number is less than x. So x is the target. In order for your hash to be within the difficulty target for the next block, it has to start with a certain number of zeros. It has to be a smaller number than the difficulty target. And that difficulty target is known by every node on the network, because every node on the network calculates that difficulty target using the same formula every 2016 blocks. Every node puts the same numbers into that formula and produces the same answer. And the way they do it is they say, what was the difficulty target for the previous 2-week period? How many blocks did we mine, and how long did those blocks take? So we're looking to mine 2016 blocks, and because we're looking to mine them in 10 minutes each, that would take, theoretically, 20,160 minutes to mine these 2016 blocks. Let's look. How long did it take? Oh, it actually took 10% longer than 20,160, which means that miners are not able to find blocks every 10 minutes. They're a bit slower. They're 10% slower, which means it's 10% too difficult, which means that the difficulty needs to be adjusted by exactly 10%. So the difficulty is reduced by 10%. Because the number of blocks, 2016, is fixed, the time it took to mine those 2016 blocks is the same. Everybody knows the answer to how long it took in minutes because they count it the same way. And therefore, they can do this division and find exactly how much to adjust the target difficulty. Everybody has the same target difficulty for the previous round. And that way, everybody knows, OK, the next block is in a new difficulty period. I expect the difficulty target for the next block based on my calculations to be x. I will only accept blocks whose hash is less than x. And everybody comes up with the same answer for x, and therefore everybody is looking for miners to achieve the same amount of proof of work for the next block based on that. That's the difficulty retargeting algorithm, which happens every 2 weeks, or more specifically every 2016 blocks, which allows everyone on the network to know exactly what the difficulty of the next block should be at any moment in time and arrive at the same conclusion. And it allows miners to know what they need to do to succeed. They have a target, and all they have to do is say, is the hash less than the target? Yes, it's a valid block. No, keep hashing. Try more nonces. See if you can figure it out. Another question is, I wonder if it's possible to guess the nonce on the first try. Yeah, it's absolutely possible. You might find it on the first try. You might find it on the 5th quintillion time try. It doesn't matter. The probabilities are exactly the same. The probability of finding it in your first try is exactly the same as the probability of finding it in your second try, the third try, the fourth try. These are independent events, meaning that the probability of each event does not affect the previous or the next event. There's no link between them. Just like if I flip a coin, whether it comes up heads or tails, the chances of it coming up heads the next time I flip it is still 50%. Even if I flip it 100 times and it comes up tails 100 times, the 101st time, the probability is 50% that it will come up heads, 50% that it will come up tails. The probability doesn't change. The same thing for picking a nonce. The chance that the very first nonce I plug in produces a hash below the difficulty level is exactly the same as the second nonce I try. I could try them randomly. I could try them in order. I could try them in decreasing order. I could start from any value of nonce randomly and then just add 1 and keep going. It doesn't matter. It makes no difference what you choose as the starting nonce and how you move from nonce to nonce. You could just choose them randomly. However, choosing them randomly involves doing some more computation because you have to figure out random numbers. And there's no reason to do that. There's plenty of randomness in the cryptographic hash. So instead, you could just increment them by 1. That's the fastest way to do it, because incrementing by 1 in binary is something computers can do very fast. So what you do is you just pick a starting point for your nonce, and you just increment by 1. And you have exactly the same chances of finding a valid nonce as everybody else on the network. And here comes an interesting question, which this is difficult to understand, but it's a very important concept on how pools work with lower difficulty. Sergio asks, why does a pool work with a lower difficulty level for its nodes to solve? If my node finds a nonce that gives a hash lower than the expected difficulty set by the pool, how does that relate to the difficulty set on the Bitcoin network for that block? This is a really, really great question. And this takes a bit of more discussion to answer so that you can really grasp what's happening. But it's a really neat trick. Let's say you have a room full of people, and they each hold 2 dice. And you have a team who are working together. And their goal is to throw dice below a certain number. And if they find below that certain number, they win. So the team wins. Let's call that the difficulty target. And that's the difficulty target for the blockchain, the whole game, right? That's the actual difficulty target. So you tell all your players, listen, everybody, we can throw between 2 and 12. Our dice, either you get 2 1s is the lowest number you can throw, or 2 6s, 12 is the highest number you can throw. We win if we roll less than 5 total between the 2 dice. So that means that 6 and 6 don't work, 6 and 5 doesn't work, 5 and 5 doesn't work, 5 and 4 doesn't work, 4 and 4 doesn't work, 4 and 3 doesn't work, 3 and 3 doesn't work, 3 and 2 works, 2 and 2 works, 1 and 2 works, 1 and 1 works. So any of those throws below 3 and 2 work, below 5. So that's the target for the whole game. And so your team starts throwing dice. But what you want to do is you want to reward the people who are throwing dice most often because they're doing more of the work for the team. How do you count whether they're throwing dice often enough? You could just wait until one of them wins. But if you just wait until one of them wins and give them all the winnings, then it's not really a pool. That's the same as if they were competing by themselves. So what you do is you come up with a pool strategy that involves giving them a portion of the reward. No matter who in the team throws a less than 5 or 5 and below, the whole team wins. But then you want to split those winnings based on how much everybody contributed to all of this dice throwing that made you a winner. So how do you do that? You set a different difficulty target, and you say, listen, every time you throw less than 10, I count 1 share of contribution to the work for you as a team member. So the team members are throwing dice. 12 doesn't count. 11 doesn't count. 10 doesn't count. 9, that's below the team difficulty, but it's not below the game difficulty. So I count 1 share because I'm doing work because I threw 9, and I keep throwing, right? Now, because the team difficulty is anything below 10, that's going to give us a pretty good metric as to who's doing the most work. The people who are doing the most work will tend to throw more 9 and below dice, and they're going to get more shares. So we're going to be able to allocate shares based on them throwing low numbers, which means they're throwing enough dice because the probability is the same. But here's the thing. A winning dice throw that is below 5 is also below 9. So as long as your people are throwing dice, the chances of them throwing below 9 are the same as the chances for any single throw as them throwing below 5. So they're not losing anything by announcing, we didn't win the game, but I did win the pool difficulty. They announce that dice throw is still helping you get closer to winning the game because they might have thrown less than 5, but it gives you a way to track their performance because they threw less than 10. So by setting these 2 difficulty levels, you have the difficulty at which we win the game, and then you have the difficulty at which your contribution as a team member is recognized and you count a share of the work. But that's less difficult to throw. Then everybody can start throwing their dice and trying to win the game as a pool. And then you can allocate the winnings correctly by counting their shares. So that's how the pool difficulty works. I hope that was understood. Dominic asks, how can I be sure that no one steals my private key by calculating it just like they do a nonce? Thank you. That's a great question. It's really, really simple. The numbers don't add up. When we're trying to brute force a nonce in order to do proof of work, first of all, that's a hashing function, but the same idea. You're trying to brute force through a space. Now, it takes quadrillions of hashes in order to do that, and that takes an enormous amount of electricity. But how many computing operations would it take to brute force a private key? So a private key is 256 bits, approximately. The maximum key is a bit less than that, but for simplicity's sake. 256 bits give you 2 to the 256 possible combinations. 2 to the 256 in decimal is 10 with 77 zeros after it. So the number you're trying to pronounce with a word is 10 followed by 77 zeros. And we don't have a word for a number that big. It's not quintillion. It's not septillion. It's not Google. It's not. There are no words for numbers that big because these are unfathomably large numbers. Let's break it down by breaking it into millions. So a million is 6 zeros, right? Great. So let's say 1 million people we're using 1 million miners to do 1 million calculations for 1 million years on 1 million planets. So how many zeros did I add up just there? 30 zeros. That was 1 million people using 1 million miners to do 1 million calculations per second on 1 million planets for 1 million years. And what they would be able to do is crank through 30 zeros of combinations, 10 with 30 zeros. They're not even halfway there because the number is actually 10 with 77 zeros. So they would need to go to an extreme that doesn't exist in nature. The amount of energy needed to simply cycle through 256 bits exceeds the amount of energy available in our solar system. It's impossible to do in terms of physics. You cannot brute force a private key. Let me put it another way. 10 to the 77 is very close to the number of atoms in the visible universe. That means that if you think about all of the atoms that make up all of the matter in all of our planet, and all of the grains of sand on all of our beaches, and every drop of water in the oceans, and every drop of water in the every molecule of air in the skies, and that's just our planet. And then you think about the solar system and all of the hydrogens there, and then you go and think about the entire galaxy and all of the visible matter that's in there, and then you think about the entire universe and all of the visible matter that's there, and think of every single atom in that. That's how big the private key is. And so it's like, pick an atom from anywhere in the universe and see if you pick the right one. It is impossible to do. So that's what the security of your private key depends on. Your private key can be discovered by someone simply picking private keys until they find one that has money in it. The only problem is there's not enough time in the universe for them to do that. Theoretically, they can do it. Practically, they cannot. There's not enough time. There's not enough computers. There's not enough energy. There's not enough silicon. There's not enough atoms to make transistors to build a computer like that could brute force a 256 private key. Mind-blowing is something you often feel when you're talking about the cryptography of numbers, or as John Gilmore once put it, there's strength in numbers, large prime numbers. And with that, we're done for today. Thank you so much for participating. This is MOOC 11, session 3. We're done for this week. I will see you next week. We have a scheduled session on Friday. Ask questions, participate in the forums, give me some great questions to answer for next time. Thank you for the participation in the chat and the live questions. Thank you for joining from all of these different countries. Lovely to see you again. Great work, everyone. See you next week.